Alright, now we're going to talk about angled projectile problems, where we fire at some angle not necessarily horizontal. In fact, these will never be horizontal, because we've treated that. Tossed at some arbitrary angle, a ball has a velocity history that looks like the figure to the right. Note that the constant downward acceleration is essentially bending the velocity, the trajectory, into the parabola that we're used to. Down here they show you how that could be, how you could have a downward acceleration even though you have velocity vectors as different things, because delta A is v2 minus v1, so tip to tail that's v2 minus v1. And we get that. The trajectory of a projectile is determined by its velocity at launch. A lot of these terminologies are going to come from artillery, because historically that's where this field was first studied. At the end of the Renaissance, the improvement in gunpowder basically meant that people had to learn how to fire things at angles rather than directly into walls, and launch the whole field of artillery and projectiles. We'll decompose the velocity into its x and y components. Usually the so-called launch angle is given relative to the horizontal. So here's the horizontal, and we say we're theta degrees above the horizontal. But that isn't necessary. When it is given to the horizontal, then we'll find that Vix is associated with the cosine, and Viy is associated with the sine. But you should always check that, because there's no reason it has to be specified that way, and the AP committee from time to time will change things just to see if you're paying attention. The fact there is now a vertical component of the initial velocity complicates things, but not terribly badly. We do need to turn the muzzle speed and launch angle into the components of the initial velocity, so to repeat that diagram, this gives us that Vix is Vi cosine and Viy is Vi sine. So let's do a sample problem. Ophelia kicks a soccer ball with a speed of 25 meters per second at an angle of 22 degrees to the ground. And it does this. How many seconds is the ball in the air, assuming the ground is level? And also, how far does it go? Because that'll be easy enough to do. So we set up all our things. We started at 0 seconds, and we start, our origin will take our leftmost points, which is Ophelia's foot. So the ball starts at 0, 0. And the initial velocity, we took what we said before, 25 meters per second times the cosine of the angle, and the y velocity will be 25 meters per second times the sine of the angle. And probably in a real problem, you would just get those numbers. You wouldn't drag them along as sine and cosine. Just my own personal tick that I tend to wait. And then the ball lands all the way out here. Ball lands all the way out here, and that is at a time tf that we don't know, at a distance r, x-coordinate of r that we don't know. But we do know that it lands back on the ground, so yf is 0 again. We know that the final velocity in the x is always equal to the initial velocity in the x, and we don't know the final velocity of the y, although we'll talk a little bit later that we really kind of do. But we don't have that given, so we'll treat it as unknown. The one that we don't have that we want is tf, so we're going to try and find an equation that lets us guess tf directly. That equation would be the y position, because I know both the final and initial y values. With our particular values, we have that it ends at 0, it starts at 0, we have 25 sine 22 degrees as the velocity times the time that we don't know, minus a half gt times squared. But now, this looks awful because we have a linear term. It's a quadratic rather than a perfect square. But it turns out that the fact that these two values are equal make life easy. We have 0 equals this stuff, and we can factor out a tf, because there's a tf here, and there's tf times tf here. And we end up with 25 meters per second sine 22 degrees, minus a half g time final. All of that times the time final is 0. And the 0 property of numbers tells us that two numbers multiplied to 0, at least one of them must be 0. But tf equals 0 doesn't make any sense. Tf equals 0 is when she kicked the ball. It can't be the time of flight of the ball. This is because our equation here is not answering when does the ball land. It's answering when is the ball on the ground. And it is on the ground at the start of the problem. So it correctly reports tf equals 0 as an answer. But we know that that's not our physical answer because it doesn't match the definitions of the problem. Note that we could factor out tf, which we just said. And then so we go through here and we say, well, 25 sine 22 minus half gtf equals 0. So half gtf equals this stuff. So tf equals 2 times 25 times sine 22 all over 9.8. The time of flight turns out to be 1.91 seconds. Now it's easy to figure out how far the ball goes, because we can take the x equation and we'll say, well, at time tf, which is 1.91 seconds, it's at distance r, started at 0, had this initial speed. And we end up with 44.3 meters. Consider the moment the ball is at its highest point. What could you say about its velocity or the components of its velocity at that moment? So pause the video and think for a couple of seconds. At its highest point, the ball is no longer rising, but has not yet begun to fall, just like before. So the vertical component of the velocity must be 0, just like before. But the ball is not at rest because it still has its horizontal velocity. All right, and that's good, because if the ball were at rest, it would just do this, which is silly. Notice that the velocity ends up being tangent to the curve here, and that will turn out to be a true thing no matter where we look. Anytime we take a tangent, that's the direction of the velocity. We can no longer say the velocity is the slope, because this is not an xt graph or a yt graph, but it does turn out that on a yx graph, you do get that the velocity is along the tangent line. So that's a useful thing. All right, now use the fact that the vertical component is 0 to compute how many meters high the ball goes. One way is to go through here, fill out our chart as we've had before. Again, starts at 0, ends I don't know where, and I don't know how high, but I'm going to call that h. Right? Remember, h is not a given, but I'm going to name the thing I want. We have the initial velocities, we have the final velocities, we have the accelerations, we have final velocities. What we don't have here is the time, so be careful, because 1.91 seconds was when the ball returned to the Earth, and this is not that moment, so that is not our time. Since we don't have the time, we might want to focus on the equation that doesn't use the time. That is the squared equation, and the squared equation in VFY says VFY squared is VIY squared plus 2AY delta y. We end at 0. We started at 25 sine 22, which we then have to square. And then our acceleration is minus g, because it's g downward. And our change in y is h minus 0. So we could walk through all of this, and we find that the height is 4.47 meters. There's another way, and some people do it that way, and that would be great. You could recognize the symmetry of the situation and say that the maximum height occurs at 1/2 the total time of flight. So the time the maximum height is 1/2 TF, or 0.955 seconds. And then I can just use, hey, I want to know where it is at that time. Let me use the equation that tells me where stuff is, that YF is YI plus VIY delta t plus 1/2 AY delta t square. With our particular values, we have a 0, 25 sine theta, 0.996, times this stuff, and we get, again, 4.47, not surprisingly. All right, this is linked into a Desmos file, so you can't play with it, that allows you to simulate this. Just plot the trajectory for any angle and launch speed, and I'll put that on canvas. Playing with it, we could ask what angle maximizes the range of the projectile, and if you played with it, you would find 45 degrees as such. Why does 45 give the maximum range? Well, there are two competing effects. At a shallow angle, the projectile moves forward very quickly, because VIX is large, but it's not in the air for very long, because VIY is small. So it doesn't get very far, even though it's moving very fast, because of how much time. And at a steep angle, the projectile has a lot of time in the air, since the VIY is large, but it doesn't move very far over, because VIX is small. So even though it's in the air for a long time, it hardly makes any distance along the ground. So the optimal angle is a compromise between those two impulses, and 45 is the one that has the two components equal to each other, since sine of 45 equals cos 45, so it is that compromise.